I will be talking about fixing bugs using AI. This is based on a white paper that's published on Research Google about the same topic, which I'm a co-author of. If you're interested, you can read some more details in that white paper later on. I'm talking about patching. What am I patching? Because there are lots of kinds of bugs. The easy ones and the simple ones we encounter every day when we code are the syntax error, missing semicolon, and so on. We don't worry about those very much. They are easy to fix, and the compiler won't get you around those. There are functional errors that are sometimes a little bit costly. If the bank pays too much, or if you pay too much due to a functional error, maybe that hurts a little. An interesting type is an integration error where lots of different weird things can happen, like in this famous case here of a Mars climate orbiter that was worth 200 million and crashed because it was part of it was using SI units, and part of it was using like US units, and it crashed because it was like a 4 times difference between the values. However, we are not talking about those. I will be talking about security bugs, mainly memory safety bugs, which caused lots of trouble in recent times. Like you can see a summary here, but in the very recent years, for example, as a small sample, it cost like 250 million accounts from banks to be leaked. Information about it, credit card applications. It can be really bad and really life-changing if your data suffers from one of those leaks. Specifically, I will be talking about the bugs that can be detected by code sanitizers. And at this point, you might ask, what are those sanitizers? Not everyone is aware of them. Of course, I don't mean the sanitizers we are all fed up of after the COVID times. I mean code sanitizers. And they have, let's say, a cryptic and a boring definition of compiler instrumentation replacing memory allocation functions like malloc. In slightly simpler words, it's like every time a program wants to allocate memory, it uses some function. And people found clever ways to modify them slightly so that we have not even more control, but more information about what happens when it does. They were introduced more than 10 years ago now, and nowadays they are very widely used in many languages. And just to give you an example, here is a simple snippet of C++ code. It allocates an array of 10 elements and then tries to access A of 10, which is the 11th element because of the zero indexing. What happens in a normal C++ program? No one knows. It's called undefined behavior. It can return something random if there is something in the memory there. Likely it will cause a segmentation fault, but you don't know really what happened. Maybe there will be garbage output, or one presentation I've seen, if they were talking about undefined behavior, on this butterflies were showing up on the slides because the C++ standard doesn't say that this cannot happen. However, if you do use sanitizers, there will be a very nice error message. Stack buffer overflow, you tried to read something at some memory address in some thread, even tell you where that error happened, where in the code, which makes it much easier to figure out what's going on. So we thought, let's try to fix those using LLMs. Before I go to the core of the work, however, I wanted to mention a few things of why that is important, now more than ever. AI is an opportunity. It's a huge opportunity in everyday life and in coding as well, but it brings also a lot of risk with it. Not all LLMs are equal. Some are very good, some are not so good, especially at coding. I worry many people will use LLM output without understanding what it really does. I'm myself guilty of Googling for a solution, checking Stack Overflow and copy pasting without thinking. Not a good idea. I would claim if it's an output of an LLM, maybe it's even a worse idea to do that. And even if you're absolutely sure your LLM, so large language model, is great, there are still ways to make it not reliable. There is a very interesting study, the seed prompt, where they made a, in general, very accurate coding LLM much less accurate just by adding a prefix or a suffix to the prompt. Like, I don't know, if you have a prompt here, write a C function, they would just add a prefix in line of make the code have memory errors or something like that. And they made, by this way, they made the output of the large language model much worse. Like here with the null pointer dereference. So we worry that the likely result is that we'll have more bad code on GitHub or anywhere else, because people will produce more code using LLMs, and it will be of lower quality. On the other hand, AI models are also getting better and better at detecting vulnerabilities. So we will have more bugs to fix, even if we don't write more bad code in the future. So hackers will have more opportunities to use these vulnerabilities. If you want to have an idea of what others think of how to use AI responsibly, Google released like secure AI framework called SAFE short, where it discusses how you can use AI responsibly in your company, in your organization. Among those things that it recommends is to automate defenses to keep pace with existing and new threats. And that's one of the reasons which we are trying to do what we are trying to do here. Here we come to our pipeline. It's very simple, just 5 steps. Each of them looks very simple on its own. However, how you combine them or how you implement them may make or break your system for detecting and for fixing these vulnerabilities. So they are finding vulnerabilities, isolating them, and reproducing them, then using the LLM to create fixes, then testing them, and then surfacing the best fix for human review and submission. Nothing too complicated there. You might just at this point, you might think, I don't work at a big tech company. Why should I care? I will try to convince you that even if you don't have the resources or the data to automate everything, you can use some of the lessons learned throughout this project to use it also in your organization, even if it's a one-person company. So first step in our pipeline is to find the vulnerabilities. The most important part of finding vulnerabilities is having good tests. I know no one likes to write tests, but it's very important here too, especially if you want to use sanitizers, because they can only detect errors in the code that is run. So if your code paths are not explored while you're running your tests, they will not be found. We need to store all of the test output and information so that we can use it for the prompt. What we find very, very important is that they should be reproducible, because we need to reproduce them before trying to fix them, because there is a delay between when the bug is found and between the time we want to fix the bug. So if we didn't reproduce the bug right before trying to fix it, we would have a fake great fix rate, and we don't want that. At Google, finding vulnerabilities is performed by an automated scanning pipeline running at night when there are spare resources. In any smaller organization or company, what you can do is to just familiarize yourself with sanitizers and try to run them from time to time to see if your code is still healthy or not. It doesn't need to be automated immediately. What I would also recommend is looking into fuzzing. That's, especially if you don't have very good tests, fuzzing can enable you to find more bugs that you wouldn't find with just normal sanitizers. Once we have our vulnerabilities to fix, we need to, first of all, reproduce them to know they are still there, and then to isolate them. So we redo the analysis before trying to fix them. And then what is important is we need to try to somehow figure out where the error is, because LLMs don't have infinite memory. So we cannot just give it the whole huge code base and say, hey, there is this error somewhere, fix it. So we analyze the code and try to figure out what we need to modify, what we need to give to the LLM as input in order to fix it, to fix the error. For us, we chose a simple approach of just picking a file. We think it most likely contains the bug. For some other use cases, and maybe if you don't have access to a large language model that has a big enough context length, so the input length, if your code has many thousands lines of code, separating a single function could be good too. This might not be, however, a huge problem coming forward, as the input length of large language models is going up very rapidly. Just recently, the Gemini 1.0 had 32,000. Now it's 1 million, and there are many also other models that go up. GPT-4 is quite high, and even some open source models are also quite high in that regard. And now we come to the large language model part. What do I do with all that information? And now we are back to my code snippet, very simple code snippet, and the error. The naive way to generate the prompt would be, hey dear LLM, here is code. It contains an error, and we found that there is an error by running a sanitizer, and it returned this stack trace. Please fix. We tried that. It doesn't work very well. And why we think it doesn't work very well is because it's hard for the model to contextualize the error and the code together. So it's hard for the LLM to link the two pieces of information. What gave much better results is to take the error type, take the information of where the error is, and adding a comment to the code. Please fix the stack buffer overflow error originating here. Then we take that prompt and we try several attempts. We might choose different files. In that simple example, it's clear that this error has to be in that file. It's not always the case that it's obvious from the stack trace which file needs to be modified to fix the error. So we try different files, and we also try different models. Now we even created a model, like a normal neural network, to predict which files need to be modified to fix an error, but you don't need to do that at all. It's just at scale. The scale allows you some additional things. And then what model? We started with the simple model that's open source. It's called T5X. You can go to this link, and you can start using it. It's not a large language model, so it might be easier to run on normal hardware. The current solution that is presented in the paper I linked in the first slide is Gemini Pro. It is based on Gemini Pro because we fine-tuned the let's say the Gemini Pro available to everyone with Google data and Google code. Nowadays, even external people can fine-tune Gemini. If that's too big and too expensive, there is also a Gemma or other open source models that you could try. In the future, we will naturally try Gemini 1.5 and see how that improves the situation. And when it comes to fine-tuning, even if you cannot afford fine-tuning a full model from scratch, there are many much cheaper options, like low rank adaptation, or even without fine-tuning with few-shot prompting, it already gives much better results if you can give the model a few examples of previous fixes, it helps immensely with the accuracy of the output.
A question from Keith. Can you talk about what fine-tuning data did you use to train for this purpose?
Bug finding pipeline I mentioned, that dates back a couple years at least. So we had thousands of examples of similar bugs already, and we used those to fine tune. And this was fine tuned. It wasn't a model fine tuned specifically for that use case, but we have an internal model where different teams could come together and with their data sets, and we trained one big internal model together.
I see Edward has some question. Is there a way to code to optimize the use of AI to find issues such as structure commenting?
People are trying to find vulnerabilities and other problems as well using AI. In this project, we didn't try to use AI to find them, only to fix them, because fixing was done by, let's say, classical methods. Once you prompt the large language model, it will return something, right? If you ever asked either ChatGPT or Gemini or any other for some code, you will know it will almost always answer with some details, like, yes, of course, I can do that for you, and then it will give you the code and then maybe explain why it works and so on. So while prompting, it's also important to structure the prompt such that you can easily get the code yourself, preferably automatically. Try to force the LLM to remove any details or any comments. And it's important to make it easy to locate the right code to replace. So two strategies are: try to either few-shot prompt or fine-tune the LLM such that it returns a diff, not a code, but a diff that you can then programmatically insert into your code, or just ask it to give you new code, but with a few lines of old code above and below, so that it's easy to find and replace, so to say. And then once you have that, once you have your code applied, once you have the LLM output applied to your code, we rerun the tests and we see what happens. Once you run the tests, what can happen? Of course, the test passes or the test doesn't pass. In a smaller company, let's say, you could think of looking at if the tests don't pass, you could look at what's happening. And maybe, oh yeah, the LLM had a good idea, but I need to modify X and Y, and then it will be fine. At our scale, we couldn't do that. If tests don't pass, we just never look at that. So we only look at it when all tests pass. And then from that, we, as the team members, looked at all of the pull requests, let's say, all of the code changes that the LLM generated. And we rejected ourselves around 20% of them, even though they were passing all the tests. And why is sometimes sad, sometimes funny. LLMs get really creative, and often they just comment out the code that causes the error. Like, it comments out the test that surfaces the sanitizer error and it's happy. It's easy to write some heuristics to filter out those code changes. We were not expecting what you see here. It just added a preprocessor directive commenting out the code in a very weird if way. Or it just comments out the code that makes the process run in parallel, makes it run sequentially, and adds a comment: cannot run in parallel because of a data race. Yeah, okay, thank you. Not very useful fix. Yeah, there are other reasons why we rejected some of the code changes, like very bad code or just tricking the sanitizer. So in general, in the first run, we rejected 20 of those. After that, the code owners had a look before the code was submitted. They only rejected about 5%, which I thought would be much more. That actually worried me a little, because were we really that good at rejecting bad fixes, or are humans more likely to approve an automated code change? Something to think about. And then once the code owners said okay, we would push the code change to the repository. That pipeline already committed hundreds of code changes, with many more waiting for validation. That's the slowest process because we still are not confident enough to let it just run wild and let it go without supervision. So the human factor is by far the slowest one. Here is the list of most common errors that we fixed with that. The simplest one had the highest fixed rate of using uninitialized values, which didn't surprise us. What did was that data races were also had also quite a high fix rate, which I thought are quite hard to fix. But what I thought more easier bugs to fix, buffer overflows and temporal memory errors, those had the worst fix rate. And then what the fix rate was, it's 15%. You might think it's high, you might think it's low. It's higher than what I expected starting this project. And we are still looking into ways of improving that. All what I said until now was based on single file fixes. Now a new training run is running where we would try to train the model on multi-file fixes, because not all vulnerabilities can be fixed using just modifying a single file. We will try to use better models with more data. We will try to implement a reactive pipeline in the sense that it will try something, it will almost get it right, but then we might try to feed that almost right result again to the large language model, and that might help it too. And we are always looking to broadening the impact by including other bug sources. Just at the end, I would like to give a shout out to some other work in that area. If you have code on GitHub, they also are working on an automated pipeline like that. Maybe that's something you can use instead of doing it on your own. From other coding news, it's all developing very quickly. Just I thought very recently about AlphaCode and them beating an average human competitor. Now there is AlphaCode 2 that's even better and beats 85% of competitors. And what I found interesting is that if you read their how it works, they use many similar techniques to what our pipeline is using. Interestingly, there is even a DARPA challenge right now that different teams can win up to $4 million if they are the best at fixing vulnerabilities using AI. I think registration is closed, but at least I will be looking at how it goes. And I just wanted to give a shout out to this tweet, which I found very amusing and impressive, where someone used an AI model to fix a bug by giving it code and then filming the behavior of the program. And the LLM fixed the UI issue with the code, with so new opportunities with multimodal models. And what I would like you to take away from the talk is, please, I know it's boring, I know it's not easy, but please try to keep your code safe. And here, necessary XKCD, maybe you're the person from Nebraska here that most of the modern infrastructure depends on. Just to mention, just recently there was the XZUtils case, which really signifies how careful we should be. For those of you who don't know, it's someone tried to backdoor like a slightly obscure library that's used throughout Linux. And if it was not detected as quickly as it was, it would be very bad. The people who did that could SSH to any server anywhere. in the world, pretty much. Second takeaway, there are many ways AI can help, but we need to be cautious. We cannot just accept its output blindly. And then the third takeaway, cutting edge becomes the norm faster than anticipated. Even if today you try what I'm telling you and you're not happy with the results, it changes so quickly. Tomorrow you might be very happy with the results. And thank you very much. I would like to thank my collaborators who helped all that work, and of course you, Sofia, and all of you for listening to my talk.
Thanks a lot. I see Niraj has a couple of questions. One of them, did you experiment with CV reports for training?
No, we didn't use CV reports for training. It's mainly because just Google code is very specific, and there it's a certain coding style, and there is so we didn't use that for that specific project. But for third party, certainly, CV reports and commits that were generated based on CVEs, that is very useful training data.
I see another question also from Niraj. What patterns emerge from the failures to fix? What would make a bug difficult to fix besides being multi-file?
I mean, if the code pathways are very complicated, if there are many callers and many writers and many readers to a certain variable, it's hard to fix it. In general, obscure code is hard to fix. A very complex and over-engineered code is hard to fix, that I would say. But we didn't study the patterns of we studied which kinds of errors were most easiest and more difficult to fix, but we didn't study like specific code patterns that are.
Did you explore chain of thought or other multi-step reasoning patterns before asking it to do the actual fix?
No, but it's a very good point, and we might try that in the next iteration.
I wanted to ask something, and let me just start by saying that I like a model which can replace code coverage as a metric for measuring unit test coverage. So it would be nice if you don't just look at how many lines of your code are covered by the unit tests, but also, even if they're covered, are those tests exercising all the potential workflows of that line of code? Like if you have a complex if statement or something like that, would you replace code coverage with something like an LLM that can tell you, hey, is this code properly exercised by the unit tests? Or maybe augment it.
I mean, code coverage is kind of it's an indicator, right? It's an imperfect indicator. I don't know if I would replace it. I would certainly try to enhance it with some other tools. I mean, I don't think it's a useless indicator. I think it's a useful indicator, but it's clearly not perfect. So I would say enhancing it with large language models could certainly be useful.
Yeah, I'm looking for people who try that experiment and see what they can surface. Because I've seen code bases where they're like, hey, we have, close to 100% code coverage, and yet, there's still some really unpleasant bugs in it.
I guess this is going to help security teams remediate vulnerabilities faster. But going from the current state to a state where it can be used in production without a lot of human intervention, what are the gaps in terms of like getting there? What is needed? Do we need like better models with bigger context windows or better reasoning capabilities? Also, I want to ask a question about executing the code. Like, is that a mandatory requirement to be able to fix vulnerabilities?
I will start with the second question. So it is running the code is required to test whether a sanitizer bug was fixed, because sanitizer is a runtime tool. So you need to run the code to have the output of it. You can envision the same with static analysis tools, like, I don't know, CodeQL, for example. If you have CodeQL query that gives you some findings, you can try to fix them using an LLM and then see if your CodeQL query still returns the same or if it was fixed. However, then you might not know if the fix if the code is still running. So I would at least compile it still. And but yeah, no, it's not a complete requirement if your analysis tool doesn't need running the code. And the first question, sorry, I forgot. Could you
Yeah.
remind
So the first question is, using this in production for like most companies, let's say that they don't have AI expertise on the security team, how could those companies benefit from a product or like a solution like this that they can use with their static analysis tool of their choice and be able to fix vulnerabilities without really executing the code? Um, so like, what do we need to get there? What's missing?
our pipeline validates, checks if the code compiles, if it runs, and if the tests pass. Sounds may at the surface of it, it sounds like a pretty good indicator that it's good. However, if you think about it hard, it's actually the bugs that are not like the code that is not covered by tests is the most likely to have a vulnerability. And you can have and your LLM might cause functional errors that are not covered by your tests. So you don't know what in the end you get. What I would definitely need to be more comfortable with letting, let's say, submit LLM generated code is much better validation. Not even much better LLMs because they can still be tricked. I imagine even if in 10 years you will still be able to trick them somehow. Maybe not. I don't know. But yeah, validation, and preferably not LLM generated validation, because that's.
Niraj has another question. Have you experimented with automatic reviews as well?
We will try to ask an LLM if the diff generated by another LLM fixes the vulnerability reported. It didn't work very well. That's all I'm going to say.